Hello and welcome to this section on velocity time graphs. During the course of this presentation, I want to give you an overview of what a velocity time graph is and how to plot and interpret one. We're also going to look at how to work out what the acceleration of an object is by looking at the gradient of the graph, and also how to determine the total distance travelled by the object by looking at the area under a velocity time graph. So, as with all graphs, the first thing to do is to look at the axes before you do anything else and ask yourself, what story is the graph telling me? Well, here on the y-axis we've got velocity in meters per second, and so this is telling us that as time is moving on, the velocity is increasing. So for example, at 20 seconds the velocity was 10 meters per second, whereas at 60 seconds the velocity was 30 meters per second. So as time moves on, the velocity is increasing. If you always do this for every graph, particularly these graphs of motion, then you're less likely to get confused between them. So your first job is always to look at what's on the x and y axis and ask yourself, what story is this graph telling? What is happening as time is increasing? Well, just as we use the distance time graph to find the speed, we can use the velocity time graph to find the acceleration. And in a similar way, we know that the acceleration is the change in velocity divided by the time taken. But we also know, just as we discussed with the distance time graphs, that the gradient of a graph is the change in the y values divided by the change in the x values. So if we look at a velocity time graph, we can see that the change in the y values is actually a change in velocity, which would be what we'd put on our top of our acceleration equation. Whereas the change in the x values would be the change in time. And so if we take the gradient of a velocity time graph, we've got values that actually represent the change in velocity over the time that it's taken, and so the gradient of a velocity time graph can be used to give us the acceleration. And that's an important point to remember. The gradient of a velocity time graph gives the acceleration. Here are three objects accelerating. Which of the three do you think has the fastest acceleration? And which has the slowest? Well, if you look at the first line, the red line, you can see that as time is moving on, its speed is increasing much more rapidly than the bottom purple line. And if we were to calculate the gradient of the red line, we would see that the gradient would have a bigger number than the blue, and the blue would have a bigger number than the purple line. So the gradient of the red line would be the steepest, it would have the biggest number. So that tells us that the object that has the acceleration given by the red line is accelerating the fastest. Its speed is changing the fastest over the time taken. So that leads us on to another point, that the steeper the gradient rather, the greater the acceleration. So you can easily tell by looking at a velocity time graph which object is accelerating the steepest, accelerating the fastest, by looking at the gradient. Now when we looked at distance time graphs, we also had a situation where the gradient was 0. And if you remember, that is because, once again, looking at the story of the graph, as time moving on, the distance wasn't changing. So let's apply that now to the velocity time graph. So we can see that as time is moving on, this time the velocity is staying the same. So a horizontal line then on a velocity time graph means that the object is moving with a constant or uniform velocity. The third thing to think about is, well, what if we have a negative slope? What does this mean? So if you have a negative gradient, you'll come out with a negative number. And if we look at this in terms of velocity, it tells us, a negative gradient tells us that the slope is going this way, and this tells us that as time moves on, velocity is decreasing. So we have a negative acceleration, and another word for a negative acceleration is a deceleration. So if you see a negative slope on a velocity time graph, then that tells you that the object is slowing down. Apologies for that. There's one little piece of useful information that we will use in some forthcoming practicals, so I thought I'd put it in here, and that is, how do we calculate the average velocity? There'll be sometimes you'll be working on a velocity time graph question, and at some point you need to calculate the average velocity. Well, like any average, it's just a case of taking some numbers on the top that represent the values you're interested in and dividing by how many values there are. So in the case of the average velocity, we start with the initial velocity and we add it to the final velocity and then divide both by 2. So that will give us an average velocity over the entire journey. Or in symbols, if you remember, U stands for initial velocity and V stands for final velocity, then we can just show that as U plus V over 2. So now let's have a look at a real example of a velocity time graph. A car accelerates uniformly from rest for 10 seconds. So that tells us right away that it's going to be starting from 0 and the line is not going to be curved, it's going to be a straight line. Then travels at a constant velocity for 20 seconds. Then the driver brakes hard and comes to a complete stop in 2 seconds. Now, in this example, we're not given any actual velocities. We're just asked to sketch the velocity time graph. Let's just give ourselves an idea of what the situation is going to look like. So, we start off by drawing our axes, remembering velocity in meters per second goes on the y-axis and time in second goes on the x-axis. So for the first part of the journey, the car accelerates uniformly, so we know we're not going to have any curves in the line, and for 10 seconds. So obviously there's no scale there, so we've just guessed that that's about 10 seconds. So you can see from this part that you could calculate a gradient for this, and you could work out, if you had enough information, you could work out what the acceleration was. For the second part of the graph, it said it then travels at a constant velocity for 20 seconds. So this means that as time is moving on, velocity is staying the same. So we can put a line something like this in. Now at the end of that 20 seconds of constant or uniform velocity, the driver suddenly brakes hard and comes to a complete stop in 2 seconds. So all of this has been 20 seconds, so it's going to come to a complete stop over a very short period of time. And so this gradient of this line here is going to be much steeper than this one here, because this took quite a lot of time. It took 10 seconds to get up to its constant speed. It took 10 seconds to get there, whereas at this end of the journey it only took 2 seconds to slow back down to 0. And so if we were to calculate the gradients, we'd see that this one is a much bigger gradient, and you can tell that because the line is steeper. Because the gradient is negative, the line is going the other way. That also tells us, just by glancing at the graph, that the object is decelerating, and in fact has decelerated or slowed down right to 0. So even a simple sketch of a velocity time graph can give you a lot of information. Now, one interesting and important value that we can get from the velocity time graph is that we can actually use it to calculate the total distance travelled. So how can we do this? Well, if you remember the equation for velocity or speed, it was the distance travelled divided by the time taken. So we've shortened it here to velocity is distance over time. If we rearrange this equation and solve for the distance, so here distance has been divided by time, so to undo this relationship we multiply both sides by time. If we rewrite this, we come up with the equation that distance is the velocity times the time. Now, if you want to calculate an area, you calculate a length by a height. You calculate the two together and that will give you the area of a square, for example. And it's exactly the same here. We want to calculate the total area because the total area under here is the velocity times the time. And so if we find the area, the velocity times the time, of all the different parts of this graph and add them together, that will give us the total distance. So how would we do this? Well, looking at that shape, it's not going to be easy to calculate the total area. However, if we break it up into sections, then the job becomes much easier. So the first thing I can do is break it into two sections. So the first section, I have a triangle. So I can calculate the area. You know how to calculate the area of a triangle using the equation half base times height. Or you could calculate the area of this square here and halve it. The second bit is a rectangle. So once again we just need to multiply the time by the velocity in this section, and that will give us the distance travelled under this part of the graph. And for the final section, once again you have a triangle shape, and so you need to use half base times height or whatever method you use for calculating the area of the triangle, and you'll end up with three distinct areas under the graph. And remember, each area is found by multiplying the velocity by the time. So we know that each area represents some of the distance travelled. So to find the total distance travelled then, we calculate each area, and it's perhaps a good idea to number them, especially in an exam, so you can show what you've been doing, and then add them all together. So once you add all those three areas together, then you'll get the total distance travelled. So that's one useful feature of a velocity time graph. Okay, here is an example that you can do. So you have some data. On the top you've got the velocity, so the velocity goes from 0 to 12 meters per second, and the time goes from 0 to 8 seconds. And so your task is to draw this graph, draw a line of best fit for each section, and then use the graph to find the acceleration in the first 4 seconds, the acceleration between 2 and 3 seconds, now this bit here, the total distance travelled, and the average speed for the 8 seconds. So you need to stop the recording now, get out your graph paper, if necessary do a quick sketch first, and then get busy. Remember that you need to use the gradient to find the acceleration in each of the acceleration parts, and you need to find the area for the total distance travelled, and you can use the equation that I showed you before for calculating the average speed to calculate the average speed for the 8 seconds. So that should take you quite a bit of time, so come back and check your data later. Okay, well this is something like how your graph should look. I've not put the calculations on because you can do that as an exercise and check with me later, but you can see that there are two different slopes, two different gradients that need to be calculated. So this one here up to 2 seconds, and then this one here up to 4 seconds. And then the rest, if you just draw a line down to there, the rest of it is at a constant velocity, and so you can, by drawing a line down to there, you can calculate the total area under this graph to find the total distance travelled. So do have a go at this exercise and check with me, and ask any questions if you're not at all sure. Alright, so I've left you there with something to do that's going to take you a little bit of time, so why not summarize what we've learnt so far then. So the gradient of a velocity time graph then gives us the acceleration, and the steeper the gradient means that the faster the object is accelerating. A gradient of 0, a horizontal line, means that the object is travelling at a constant velocity. And if the graph is linear, or the section of the graph is linear, that tells us that the acceleration is constant. If you see a curved section, that tells you that the acceleration is changing, and so we have to use different methods to calculate the acceleration in that case. So you can see that it's very important not to get mixed up between distance time graphs and velocity time graphs, because the gradient and the meaning of the 0 gradient are completely different. If you follow my hint and always read the story of what the graph is telling you, ask yourself what is happening as time is moving on, then you're less likely to get confused in an exam. But please make sure that you're clear on the differences between the two types of graph. Well, I hope you enjoyed this, and I look forward to seeing your completed graphs and calculated areas very soon.